Hey everyone, and welcome to this explainer. If you're gearing up for your Cambridge A-level physics exams, we are jumping right into section 18 of the syllabus today, electric fields. Now, I know these invisible forces can feel, well, kind of abstract, but stick with me. As we break this down, we're going to see exactly how they work, and more importantly, how you can absolutely crush these questions on your exams. To make sure we're laser focused, we are anchoring this entire explainer directly to the official Cambridge syllabus document. This guarantees that every single concept, formula, and definition we talk about is exactly what you need to master for the 2025 to 2027 exams. So no fluff, no distractions, just the pure, high-yield physics you need. Okay, here's our roadmap for today. We'll start with defining electric fields, move into uniform electric fields, tackle point charges and forces, and wrap up with electric potential and energy.
Let's dive into part 1, defining electric fields. It's really fascinating to look at the precise wording the syllabus uses here. An electric field isn't just some vague area floating in space. It is explicitly defined as a field of force, and specifically, it's the force per unit positive charge. That word positive is absolutely crucial. When we draw those field lines with the little arrows, those arrows are showing you the exact path a tiny positive test charge would take if you just, dropped it right into the middle of that field.
And that perfectly sets up our first key equation. If the electric field, E, is the force per unit charge, then the total force on a charge is simply the charge itself multiplied by the electric field strength. F equals QE. It's literally that simple. If you know how strong the field is and you know how much charge you're dealing with, you instantly know the mechanical force pushing or pulling on that particle. All right, moving on to part 2, uniform electric fields. So a uniform field basically means the field strength is exactly the same everywhere inside a specific region. The classic way to build one of these is by setting up two oppositely charged parallel metal plates. For these uniform fields, the field strength, E, is just the potential difference, or voltage, between the plates divided by the distance between them. E equals delta V over delta D. What's super cool here is that you can physically control the force on a particle just by tweaking the voltage on a battery or simply moving the plates a little closer together. This exact principle is literally what steers electron beams in older televisions or guides ions in those massive particle accelerators. Now, uniform fields between nice straight plates are relatively straightforward. But what happens when the field isn't uniform? How do these mathematical rules change when we look out into the wider universe, where a single charged particle is just sitting there in free space, radiating a field outward in all directions, like a glowing light bulb? Well, that brings us right to part 3, point charges and forces. If we look at syllabus sections 18.3 to 18.5, we get a ridiculously helpful simplification to start off with. The syllabus says we need to understand that for any point outside a spherical conductor, like, say, a charged metal dome, the charge on that sphere acts as if it's a point charge concentrated entirely at its exact center. Basically, scratch the incredibly complex calculus for the 3D shape of the sphere. We just get to treat it as a single, infinitely small dot of charge in space. Such a massive time saver. And it is really cool to see how Coulomb's law steps in here to calculate the specific force between two of these point charges in free space. The force, F, equals the product of the two charges, Q1 and Q2, divided by 4 pi epsilon naught r squared. Now, since E equals force divided by charge, the formula for the electric field generated by a single point charge becomes E equals Q over 4 pi epsilon naught r squared. Notice that r squared sitting in the denominator? That is huge. It means as you move away from the charge, the field doesn't just drop off steadily, it drops off exponentially. Double your distance, and your field is literally 4 times weaker. You absolutely have to know the difference between these two models for your exams. A uniform field strength relies entirely on the voltage and the physical distance between the plates. It stays constant everywhere in that gap. But a point charges field, that is highly dependent on exactly where you are standing. It weakens with the square of your radial distance from the charge. So whatever you do, do not mix these two up. Okay, let's head into our final stretch, part 4, electric potential and energy. So instead of just looking at the push or pull of a force in a single frozen moment, electric potential is all about energy and effort. The syllabus defines electric potential at a point as the work done per unit positive charge in bringing a small test charge all the way from infinity to that specific point in the field. Think about trying to push the north poles of two magnets together. The closer you get, the harder they push back, right? Pushing a positive test charge toward another positive charge is the exact same thing.
It requires real work, and that work gets stored as potential energy in the field.
So how does all this energy tie everything together? Well, first, the electric field is literally just the negative of the potential gradient. It's basically the slope of the energy hill. Second, the actual potential, V, due to a point charge is Q over 4 pi epsilon naught r. Notice it's just r on the bottom this time, not r squared. And finally, if you want the total electric potential energy, EP, between two charges, you just multiply that potential by the second charge. So you get Q times Q over 4 pi epsilon naught r.
Look, I know we just threw a ton of letters and math at you. To save you from formula overload, this summary is going to be your absolute best friend. It perfectly standardizes all the foundational equations we've conquered today for force, field strength, and potential energy, split right down the middle between uniform field rules and point charge rules. Take a screenshot or write this down. It's exactly what you'll want to review the night before your test.
As we wrap up, I want to leave you with one final, kind of mind-bending thought to chew on. If the electric field is merely a physical reflection of a changing energy gradient, how does that reframe your understanding of the physical space around you? What other invisible hills and valleys of potential exist out there in our universe, silently dictating the motion of everything from microscopic electrons to massive swirling galaxies? Keep that curiosity alive as you continue studying physics. Thanks for joining me on this explainer, and good luck mastering those fields.